Hey everyone, so this is a little lesson on the intermediate value property and continuous functions, and if you've never watched my videos before, I highly recommend you pause and try the examples when prompted. Also, there are always free guided notes available at dividingconquermath.com, and hey, while you're here, maybe I have been finding my videos helpful. If you're looking to give me some help with my channel, it would be great if you could like my videos, or even better, if you could subscribe to my channel. Leave me a comment if there's ever any feedback, things that you want to continue to see, things you wish you could see more of, and also tell your friends about my channel. I'm trying to build a nice free resource for everyone of quality math help. So let's talk about the intermediate value property. So this is when a function has all of the values in between 2 points A and B. So what does that mean? So here's a graph. So I've got these 2 points marked here, A and B. And so what the intermediate value property says is that basically you have kind of this. So just all the values are filled in. So maybe put another way, what can't happen is you can't have something like this happen. This would be a function that does not have the intermediate value property. So it's got to be all filled in. And it doesn't have to look like this. It can look like whatever. But you get the idea. Okay. So from the intermediate value property, we actually get two consequences when we have that, and we're also thinking about continuity. So the first consequence is what we call connectedness, and it's consequence, but not like a bad consequence. It's just, it happens to be two things that we get out of this. So what connectedness means, it's actually like something pretty obvious, I think. It's saying that a graph will be a curve without any breaks. So one of the consequences then is that you have to have this, you can't have this. So that's the idea of connectedness. So like I said, like it seems weird that we point that out, but there are certain exercises where this will come into play. So I'll show you that in a moment. The other consequence is what we call root finding. So a root is a solution to, if you have a function and you set it equal to 0, that's what's known as a root. So it's anything that makes the function equal 0. Okay, so if a function goes from negative to positive or vice versa, then we know it has a root. So here's what I mean by that. So we've got the intermediate value property. So here are my 2 points. I've got A and B. And so notice, so A is positive and B is negative. So the y values, right? The y values are positive and negative. So what this is trying to say then is if I have the intermediate value property here, then as I'm going through, basically what's got to have happen is I've got to have a root. So you see right there, I have that root. So that's guaranteed to happen if your function goes from positive to negative or vice versa. Then you've got to have a root. And you don't have to have just one root, by the way. So I just drew one random function, but here's another one. So this one is going up and down, up and down, up and down. So it can go up and down as many times as it wants. Functions can do whatever they want. So this one has lots of roots. So I circled all of them. So anything can happen, but you're guaranteed to have at least one root. So that's the other consequence. So there's two exercises that typically come up that are kind of related to these properties. So the first one is this one. So this is kind of a strange question maybe, but it says, what value of A makes this a continuous function? So notice this is a piecewise function, and a lot of times people think that piecewise functions mean that they're not going to be connected. But what we're actually trying to do is we're trying to manipulate this piecewise function to force it to be connected. So here's what I want you to do. First, let's just try to graph out what's actually happening here. So I'm going to just draw a few points. So I want to draw this part here, just the top part, x squared plus 1. So what are a few points on this? So let's see, I'll just do this. And so let's see, this has to be for x is greater than 2. So let's see, at 2. Here would be 1 point. And then this is a parabola. So it's going to kind of continue to open up this way. Okay, so here's what I know about this graph. It has this one part here, and I have this other part of the graph ax, and this starts at a is less than or equal to 2. So normally with a piecewise function, so I'll intentionally draw something like what people usually think of. We usually think of piecewise functions as something like this, right? They're not connected, or maybe I guess the point here would have to be filled in. But specifically what I'm looking to do here is I'm trying to make sure that this first point is actually connected to this empty one. So what I want to do then is I actually want to set these two functions equal to one another. So let's start there. So I've got x squared plus 1. I want this to equal ax. But I need this to happen at a specific point. So that specific point is here at 2. So I need to plug in 2. So if I plug in 2, this will give me 4 plus 1 equals 2a, right? So that's just me plugging in 2 for all the x's. So now I can actually look at this and say, oh, I can solve for this, right? So this is 5 equals 2a. So my a that I need for these to be interconnected would be 5 over 2a. So what this means is if I'm going to kind of write a specific piecewise function that will be connected, then it would be the one, so I'll get rid of this now, and it would be 5 over 2x. That's kind of what this is getting at. So that means then right here, I have this overlap, and let's see, I would go up 1, 2, 3, 4, 5, and over 2. So it would be something going like this. So I know that's kind of a little bit messy, but hopefully you kind of get the idea. So this is what you're basically trying to force to have happen. So I have more examples of this. So this is just one to kind of get the idea, but if you're looking for more, you can check out those videos. And here's the other type of question that kind of comes up with the intermediate value property. So show that this equation has 3 solutions in this closed interval. So basically, what we want to do is we want to think about, so we want to actually kind of go in pieces here. So if I go, let me use white here. So if I go from -4 to 3, so here's what I want to do. I just want to notice the value of this function from, say, -4 to 3. So let me call this f of x. And actually, let's not do this like this. I'm going to set this up in a table. So this will be my f of x. So what I'm going to do is I'm going to have x, and I'm going to plug this into this table. And this is a little bit of an experiment. So what I'm going to do is I'm just going to grab a few random values, and let's see, I'll continue on over here. So I'm going to just fill this in. So let's do this for 1, 2, 3, and 4. Okay, so let's start there. Let me fill this in. So I'm just going to plug this right into the function. Okay, so this is kind of a clunky way to approach this, but it kind of helps illustrate my point. So if you're given a function on some interval and you're just trying to figure out, does it have a root? So you can kind of play around with the function like this, and what you're looking for is where the signs change. So what I mean is I go from -6 to 17. So somewhere in here, there is a root. So this would be 1 root. Okay, so then I don't have any sign changes until I get from here to here. So let's see, this is the second root, 2 roots. And then I stay negative until I get here. So here's my 3 roots. So here's how I can tell them that I have 3 solutions or 3 roots, is because I see that there are 3 sign changes within this interval. Now, it's totally possible, by the way, like this kind of worked out pretty conveniently for us. It's not always the case that it's going to happen on whole numbers. You could actually have something far less convenient, like maybe you have your sign change somewhere between like between -4 and -4.5, and then maybe from -4.5 to -5. Like you could have 2 sign changes in like one of these intervals. But a lot of times when you're doing these problems, a lot of times, not always, but a lot of times the textbook wants to make it so that you can easily find them just to kind of make the point. So we can see here that there are definitely 3 solutions. Okay, so that is it for this video. So it's kind of just a quick overview. If you're looking for more examples, I do have plenty of example videos. Any questions or comments, drop them in the comments below, and I'll see you guys next time. Thanks for watching.